What is a lunar month? Many of you probably know that a lunar month is the amount of time it takes for the moon to complete one orbit around the Earth. The moon's existence, in fact, is the reason why so many different cultures around the world developed the concept of a year subdivision that's more or less a revolution of the moon, what in English we call a month. Now, here's the next question. How long is a lunar month? Someone has probably told you a number for this at some point in your life. Chances are, someone told you it was 29 days. But there's also a good chance you remember someone telling you it was 27 days. You might even remember both of these figures given to you by different people. What's going on with that? Is a lunar month 29 days? Or is it 27 days? Or is it something else? Welcome to TwoLambdaPlusBlack. I am Heirua. What is a lunar month? Well, we just went over that, right? It's the amount of time it takes for the moon to complete one orbit around the Earth, right? Right? How do you measure that the moon has completed exactly one orbit around the Earth? Well, you just see that it made it back to the same place in its orbit, right? This blue eraser is orbiting this yellow eraser on this sheet of paper. If you wanted to know when the blue eraser has completed one orbit, you could look for when the blue eraser returns to the same coordinates on this sheet of paper. Some number of units from the top, some number of units from the left. But what if the sheet of paper did not have an edge, but rather extended infinitely in every direction? Well, if you stood on the surface of the yellow eraser, you could keep staring at the same spot in the sky where the blue eraser was and measure how long it takes for the blue eraser to come back. But what if this yellow eraser you are standing on was itself rotating? In fact, imagine a universe where there were only these two objects and everything was a perfect circle or a perfect sphere perfectly aligned. Does there actually exist a way to differentiate the blue eraser completing one orbit from the blue eraser completing 3/4 of an orbit and the yellow eraser rotating 1/4 a rotation in the opposite direction? And what if the yellow eraser was itself moving through space? Fortunately, here in the real universe, there are plenty of complicating factors and imperfections to make for various references for measuring one orbit. If the orbit of an object around another object is not a perfect circle, then one could define a complete orbit as being from one apsis to the next instance of that apsis, where an apsis is the point in an object's orbit where it is farthest from or closest to the object it orbits. This defines the revolving object's anomalistic period. The moon's orbit around the Earth, in fact, has eccentricity, and one anomalistic period, conventionally measured as from apogee to apogee of the moon around the Earth, is called an anomalistic month. If the axis of an object is not perpendicular to the plane of an orbiting object, then one could define a complete orbit around this object as being from one equinox to the next instance of that equinox. Usually, when we talk about equinoxes, we're referring to the Earth with respect to the Sun. But we could extend this concept of equal hemisphere exposure to the Earth with respect to the Moon. The length of this orbit is the revolving object's tropical period. The Earth, in fact, has an axial tilt, and one tropical period of the Moon around the Earth is called a tropical month. If stars are visible in the sky, and this field of stars is relatively static in apparent position with respect to each other, then one could define a complete orbit as a return to the same position with respect to the field of stars. This defines the revolving object's sidereal period. One sidereal period of the moon around the Earth is called a sidereal month. If Object 3 orbits Object 2, while Object 2 itself orbits Object 1, then if the plane of the orbit of 3 around 2 is not coplanar to the plane of the orbit of 2 around 1, then one could define a complete orbit as being from one ascending node to the next ascending node, where an ascending node is the point at which object 3 moves from south of the orbiting plane of object 2 to north of that plane. This defines the revolving object's draconic period. One draconic period of the moon around the Earth is called a Draconic Month. What is also possible when object 3 orbits object 2, which in turn orbits object 1, is to define a complete orbit in terms of the angle between the line connecting objects 1 and 2 and the line connecting objects 2 and 3, or more precisely, the angle between the former and the projection of the latter onto the plane of the former. The time it takes for one instance of this angle being 0 degrees to the next instance is object 3's synodic period. If that explanation sounds too complicated to you, the Sun-Earth-Moon system has the nice property that the Sun is an emitter of light, which travels in straight lines, thus elegantly manifesting these angles as phases of the moon. The time from a new moon to the next new moon is a synodic month. And in fact, most of Earth's cultures that develop the lunar or lunisolar calendar use specifically the synodic month. After all, the phases of the moon are more salient than the position of the moon among the stars needed to define a sidereal month, which itself is much more salient than eccentricity, inclination, or axial tilt. So, to recap, the time from one specific apsis to the next is an anomalistic period. The time from one vernal equinox to the next is a tropical period. The time from one star-field position to the next is a sidereal period. The time from one ascending node to the next is a draconic period, and the time from one specific phase to the next is a synodic period. It's always great when you can measure or work out a quantity in multiple ways so that you can double-check your work. Let's just make sure all of these definitions measure out to the same numbers for the moon and... oh no. These numbers aren't just not all the same, they are all not the same. Not one pair of these 5 different lunar months have the same length. This isn't a mistake though. These are the actual lengths of a lunar month via these different definitions. But these definitions all seem like they're validly describing one complete orbit of the moon around the Earth. How could they have differences? If you wish to, you could pause the video at this point to try to think about where the nuances among these definitions lie. It's okay if you don't figure many of the nuances out. They could be quite tricky. The easiest difference to figure out is why a synodic month should be different from the other months. Since the Earth is itself moving along a circular orbit as the moon revolves around the Earth, the next time the moon comes into an angular alignment with respect to the Sun, the alignment itself is already at a different angle with respect to the cosmos around. To complete a synodic orbit with respect to the other orbits, the moon has to cover more ground because the goalpost has itself moved forward as the Earth significantly progressed along a circular orbit, an amount equivalent to about 2 days. The differences between the lengths of the other 4 lunar months are attributable to the phenomenon of precession, whereby an axis of a rotating object wobbles due to an external force. Precession is commonly demonstrated with a top. If you've ever spun a top, you might have noticed that the axis around which the top spun points in a different direction over time, generally tracing out a circular path. You might have heard that Polaris was not the ancient Greeks' North Star, because back then, the Earth's North Pole, in fact, did not point at Polaris, because the Earth's axis wobbles like a top's axis, completing a precession approximately every 26,000 years. But precession doesn't just stop with the axes of objects. Their orbits precess too. The sum effect of all precessional effects is that the Draconic month is slightly shorter than the tropical month, which is a tiny amount, just 7 seconds shorter than the Sidereal month, which is slightly shorter than the Anomalistic month. So is 27 days or 29 days a lunar month? Yes. It's also worth noting that these figures are averages over time, and that each individual orbit could be slightly less or more than the average. Synodic months, for instance, fluctuate between 29.3 days and 29.8 days currently. On another note, you may have also heard the length of an Earth year quantified as either 365.24 days or 365.26 days. Once again, both are correct. A tropical year is approximately 365.24 days, whereas an anomalistic year and a sidereal year are approximately 365.26 days. The time from one spring to the next spring is on average shorter than the time from one point with respect to the stars to that point again. If you celebrate your birthday according to the conventional Western calendar, then you are celebrating your birthday with respect to Earth's seasons, as this calendar follows the tropical year. If you instead celebrated your birthday with respect to the stars, your sidereal birthday, if you will, and you live, say, 80 years, then the difference between a tropical and a sidereal year will mean over the course of your life, you'll on average need to push your birthday one tropical calendar day later. The anomalistic and sidereal years, on the other hand, are so close together that you'd have to live until the age of 306 for them to separate by one whole day. So unless you're a Greenland shark, you can probably just copy-paste your sidereal birthday as your anomalistic birthday. I'll end this video with a question to ponder. Does it make sense to talk about a Draconic or Synodic year? Thanks to all of my patrons for funding my work. If you would like to join them, head on over to patreon.com/heirua. There is a link in the description. And as always, remember to love the night.